Good morning, class, and welcome to this lesson on Electrostatics 10, Equipotential Surfaces continued. Today we will be able to derive the equation for electric fields and draw a graph of potential versus distance. Okay, so I'm going a little bit out of order. I'm sorry about that. I'm just going to do it this way. So this picture right here, even though I have not gone over it yet, I will go over it in the next video actually, is a picture of a capacitor. And with this capacitor, we see we have two plates. And these plates are equal and opposite charges. Okay, and what we want to know about a capacitor for the purposes of this lesson is that inside a capacitor, we have a uniform electric field. We have a uniform electric field inside a capacitor, meaning the electric field doesn't change from one spot to another. Unlike a point charge, the electric field decreases, positive, as the further we move away from the point charge. But in here, the electric field remains constant. So inside this capacitor, because the electric field is constant, the perpendicular to the electric field are equipotential surfaces. So these planes here are of the same potential. Okay, and so we want to know the electric field is inside these surfaces. Well, we start off with the basic equation that delta V equals negative work over Q. And we know that work is equal to force times distance over Q, delta V. And we know that F over Q is equal to the electric field. So delta V equals E times D. So this is going to be one of the equations we use to solve for the potential difference or the electric field when we're talking about equipotential surfaces. So this is going to be our equation right here. Memorize it. Okay, in this picture they use delta S because in our book delta S is for distance, but you can just put D right there, that's fine. Okay, so once again, this is the equation to solve for electric field or the change in voltage if we have two equal potential surfaces and we know the distance between them. Okay, so that's going to be the equation we use in class a lot. The next thing I want to go over is graphs. Let's go back to a regular equal potential surface. So we have a sphere. We have a sphere again, and it's an equal potential surface. Okay. What is a graph of the potential going to look like here? Remember we talked about electric fields. And so if we have an electric field versus the distance away, this being R, the electric field inside a conductor is going to be zero. So it's going to be zero until we reach R. And then after we leave here, this is positive, it's going to decrease rapidly because we can do this as V equals K Q over R squared. Remember, an equal potential surface we can treat like a point charge. We can treat it like a point charge. Obviously, it's not a point charge because it has a radius, but it still obeys the same laws. So V equals KQ over R squared here. Well, what about potential? So far we've gone over electric fields. What about potential? And what we need to know about potential is that inside a conducting sphere, inside a conductor, potential is the same throughout. Potential is the same throughout. So if we had a graph here of potential versus radius, remember potential is going to be V equals KQ over R. So it's going to drop off not like a curve, but it's going to drop off more like a straight line because it's 1 over R. But because it is the same throughout, the graph is going to look more like this. Okay? And this is going to be for a positive test charge,